That was what you just did.
I got it.
Okie dokie. Today, I have no idea. Today, we are talking about the history of the atomic model. Okay? I have a video. The video didn't work very well in first period. Maybe it'll be better for y'all.
It'll work better.
Okay.
Yeah.
Okay. We'll take that. All right, see the atomic model.
Are we getting these back?
I had a worksheet. I have one of those doodle notes, but I forgot to print it out, so you all will just have to take regular notes today. I will point out the exact information that you need to know for each of these scientists, discoverers,
People.
philosophers. It is. It's like, yeah, I
can't
don't
remember names.
like history, so I've been dreading this, but first period went okay. So it's not too bad.
History. You don't gotta know people's names.
True.
Well, sometimes.
Yeah, I think you'll be able to get this. They've got some weird names here. All right, so the objectives of this lesson today. Who were some of the key figures that contributed to our understanding of atoms? Kind of. What were the significant discoveries that shaped atomic theory? So the progression of discoveries from like Leucippus, Democritus, Aristotle time to where we're at today. What were those significant discoveries? If the Bohr model, you'll find out what that is. If it has been replaced by something more workable, why do we still use it? We'll discuss that. How does the most current atomic model depict atoms? What does it show that they look like? Yeah, I feel like this was a given. I don't know.
Sure.
How does workability or accuracy drive the development of models? You just make them mo better, is the answer. Use technology and more accurate scientific instruments and experiments to make your models more workable, more accurate, mo better. Okay, I'm gonna turn the lights off. Don't fall asleep. First period, fall asleep.
Really? You know what you should get? You should get one of those tiny little Nerf guns. Mr. Daddy likes to shoot them at people when they fall asleep.
I like that. I should do that. Okay, this is a guy. He's kind of nerdy, but he's really smart. I really like his video. Pay attention. I hope the Roku cooperates this time.
As scientists have done experiments and learned more and more about atoms, they've changed the way they think about atoms. So in this video, we're going to look at a timeline of the different ways that scientists have pictured or imagined atoms over the years. Now, the first people to really talk about the idea of atoms were the ancient Greek philosopher Democritus and his teacher Leucippus. They lived about 2,500 years ago. And Democritus, he said something like this. He said, imagine you have an object, like say a slice of bread, and you cut that in half. And then you take half of that and you cut it in half. And then you take half of that and you get the idea. Eventually, he said, you're going to come to something that you can't cut in half anymore. And he called these objects, he called them atomos, which means uncuttable. And it's where we get the word atom from. Democritus imagined that all matter, all stuff, was made of these tiny, uncuttable particles. And he imagined that the atoms came in different sizes and different shapes. He imagined, for example, that iron atoms had hooks, which is how they could hold together so strongly. And he thought that salt atoms had spikes on them, because he felt that salt tasted sharp. So, Democritus was right. But people didn't really take to his ideas. Part of the reason was because around the same time, the well-known philosopher Aristotle proposed his own idea of what matter was made of. He said that different things were made of different amounts of the elements earth, water, air, fire, and ether. This is kind of like Captain Planet, if you're old enough to get that reference. And more people believed Aristotle, maybe just because he was so popular already. So Democritus and Leucippus, they were right all along. But here's the thing. They weren't scientists. They couldn't do experiments in the laboratory to prove that they were right. And because of this, some people think that their idea, it was just kind of a lucky guess. They couldn't actually prove what they thought. So, how can you tell whether it's right or wrong? Ideas about atoms remained that way for about 2,000 years, until in 1808, the British chemist John Dalton came up with the first scientific experiments that showed that matter was made of tiny little particles. This is kind of how John Dalton pictured atoms. He imagined them sort of as tiny little balls that arranged in different combinations to make different things. And he imagined that these atoms were indivisible. You couldn't cut them into smaller pieces. Now, at first, nobody believed Dalton. But over the course of the 1800s, more and more scientists did begin to believe what he had to say. But then in the 1900s, the early 1900s, people's idea about atoms started to change. One of the key things that caused this change was that in the late 1800s, J.J. Thomson discovered that atoms have electrons. And he discovered that electrons are much, much smaller than atoms. So while Dalton thought that atoms were tiny and indivisible, J.J. Thomson said, no, they're not indivisible, because they're made up of electrons, which are much smaller. So J.J. Thomson pictured the atom as sort of like a blueberry muffin. He called this the plum pudding model. J.J. Thomson imagined that if you took an atom and split it open, you'd see tiny electrons stuck throughout the inside of it, just the way blueberries are stuck in the dough of a blueberry muffin. And Thomson thought that what's the dough in a blueberry muffin? That it was like a positively charged substance. So you had negative electrons stuck in like a positively charged dough. And together, the positive and negative charge balanced, the two things balanced each other out so that the atom was electrically neutral. But the big change from Dalton's model to Thomson's model was showing that atoms weren't actually indivisible, that they were made of even smaller things. Now, not too much longer, in the gold foil experiment, Ernest Rutherford discovered that atoms had a nucleus. That all the positive charge in an atom was concentrated right in its center, and that besides that and the electrons, atoms were pretty much empty space. So J.J. Thomson thought the positive charge was all distributed throughout, like dough in a muffin. But Rutherford showed that all this positive stuff was concentrated right here in the center. And this is what we call the nuclear model of the atom, because it has a nucleus. Sometimes people call this the Rutherford model. Now, so far we've been talking a lot about the positive charge and the nucleus of it. But we haven't talked too much about what's actually going on with these electrons in the atom. And in 1913, the physicist Niels Bohr came up with his model of the atom. He reasoned that there was a nucleus in the middle, just like Rutherford had, but that electrons, instead of just sort of being randomly distributed throughout the atom, Bohr said that the electrons were sort of like planets around a sun, that they were spinning around the nucleus in circular orbits. So here are a picture of some of the electrons, and here are the orbits. Imagine that they're spinning around the nucleus in these circles. All right. Now, people thought Bohr's idea for the electrons made a lot of sense at first, but then in the 1920s, additional experiments showed that it wasn't exactly the way electrons really move. And a variety of physicists, particularly the physicist Erwin Schrödinger, showed that electrons weren't really spinning in orbits, but it's more like they were hyperactive flies, and they were buzzing around the atom, sketching out different shapes. It's kind of if you did like time-lapse photography on a hyperactive fly, and you saw that over a long period of time it sketched out a particular design. And whereas Bohr called these circular paths, he called them orbits, Schrödinger called the hyperactive sketch-out shapes, he called them orbitals. Here's a circular orbital too. But electrons didn't only make circles. This is actually a sphere because it's a circle in 3 dimensions. Here is another shape, another type of orbital that electrons could also make. Looks like this, sort of 2 teardrops next to each other. So in the quantum mechanical model, electrons don't orbit the nucleus. They buzz around the atom, sketching out different shapes. Now let's focus on the nucleus here. Over the same amount of time, and a little bit later, scientists were discovering the 2 subatomic particles that make up the nucleus. So we can refine this picture a little bit more. In 1919, Ernest Rutherford discovered protons. There they are. And then in 1932, James Chadwick discovered neutrons. So the really correct view of the quantum mechanical model shows the orbitals being sketched out by the electrons, but then also shows the subatomic particles, protons and neutrons here in the nucleus. Now, this is pretty much how we think about atoms today. But as scientists learn more and more about atoms, as they do more experiments, they're going to find that this model isn't exactly a perfect representation of what atoms are really like, and they're quite likely to change this and refine it even more. Now, as I said, this quantum mechanical model is like the really accurate way to describe atoms. But the thing is with these orbitals, it can really be kind of a pain sometimes to describe simple things that atoms are doing using electron orbitals. And so a lot of times in these videos, when I talk about atoms, I'm actually going to be sort of using a cross between the very correct quantum mechanical model and the sort of outdated Bohr model. Just because for our purposes, a lot of the simple things we're going to be talking about, the Bohr model, it works just fine. So already you've probably seen me draw atoms like this, where you see the electron orbits at different angles, and sometimes, particularly when we're talking about bonding, we're going to be drawing atoms like this, with the protons and neutrons here in the nucleus, and then electrons in different rings, different orbits on the outside of the atom. We're going to find that thinking about the atom like this is very useful for simple tasks, talking about bonding and stuff. But keep in mind that when we're discussing atoms, they actually aren't exactly like this, and they're much more like the quantum mechanical model. So keep in mind that I'm lying to you a little bit, but I'm lying to you in order to make it easier to convey some fundamental topics.
Okay, wake up. Yeah.
So can you just keep breaking it down, even when it's microscopic, can you keep breaking it down? It's like in a microscope.
Not infinitely that we know of. I mean, some scientists later on could discover a way to magnify a quark. A quark is like the smallest thing on our planet. And that scientist could just discover that quarks are made up of something else. Okay? All right. So to recap, all right, these are things that I want you to remember. We're going to start back in 460 to 370 BC. Okay? This is the time of Leucippus, Democritus, and Aristotle. Okay? This is the beginning of atomic theory. So Democritus and his teacher Leucippus, or Leucippus, depending on however you pronounce your C's in Latin. All right, they theorized that the world is made up of tiny particles that could not be broken down any further and called them atomos, which means indivisible or uncuttable, like the video said. So that was where the teacher in the video described like a loaf of bread. You cut it in half, and you take half of that, cut it in half, and you keep doing that until you can't cut it in half anymore. That's what they theorized that atoms were. They were the smallest thing that you could possibly get. All right, you couldn't make them any smaller. That the world, like, that there was nothing smaller than an atom. Okay. All right, so Democritus also thought that the shape and texture of atoms varies depending on the type of matter in which they're found. So if you look up here, it might be hard to see. So for instance, it shows like this atom has hooks on it, okay? And he theorized that solids have hooks in them to help them like Velcro, where they're stuck together more. Whereas like a liquid is slippery, like water. And then he also theorized, like you heard in the video, salt that has spikes on it because he said it tastes sharp. So he used the best information that he could in that time. They didn't have electron microscopes or cathode rays to try to determine any further characteristics of these atoms. But he used his sense of taste and his sense of sight and all of his five senses to observe what he could about matter. Okay, and this is what he theorized. So, for example, he theorized that atoms in a solid have hooks and water atoms are slippery. And go. Okay. In contrast, you have Aristotle, a really well-known philosopher that was known for theorizing a lot of concepts in other areas. So Aristotle had his theory that matter was continuous and not made of discrete particles, where he thought that you could keep dividing it infinitely, kind of like what Zach was saying. Okay, and as far as we know now, you can't. Okay, the farthest that we can divide matter is into a quark, Q-U-A-R-K. We're not going to talk about that in this class. But this is what Aristotle thought, that matter could be subdivided indefinitely. You can subdivide it an unlimited number of times. But he was proved wrong as far as we know, as far as our scientific experimentation goes. Okay, but it's like science in theory, science is always changing, always evolving. The better our technologies get, the better our instruments get, the smarter we get, we can always change our theories on something. Okay. So that was Aristotle in opposition to Democritus. All right, so then 2,300 years later, we have a scientist named John Dalton that comes into the picture, and he's like, you know what? I think Democritus was right. I think that all matter is made up of atoms. And his model was of tiny indestructible spheres that had little structure. He just pictured atoms just like little balls, right? You got a little ball of iron, you got a little ball of hydrogen, right? But they were different only in their mass, okay? So John Dalton theorized that the atoms of one element are different than the atoms of all other elements, especially their masses. He didn't know at that time that was because it differs based on the amount of protons and neutrons that are in the nucleus. He just knew that an iron atom had a bigger mass than a hydrogen atom did. He just didn't know why. Because the scientific instruments and the technology at that time, he didn't have anything available to help him learn what was making the masses different. So all he knew was that they were different, he just didn't know why. So he believed that atoms combine chemically in small whole number ratios, i.e. the law of definite proportions. How for instance, every water molecule has 2 hydrogen to every 1 oxygen, okay? Those ratios. So that was John Dalton. John Dalton solidified the idea that Democritus was right about atoms. Okay. So by the end of the 1800s, scientists knew that there were 2 forms of electrical charge, positive and negative. Opposite charges, so positive is attracted to a negative charge, positive is repelled by a positive, negative is repelled by a positive. Okay. They discovered that, which led them to discover electrons. Okay, electrons were discovered first. This law, electrostatic charge, you don't really need to know that. Okay. Just know that because of the discovery of the law of electrostatic charge that led us to the discovery of electrons. So electrons were first. And the scientist who was credited with discovering electrons, with discovering that atoms can be broken down further, because prior to this, they didn't know that atoms could be broken down into smaller pieces. Just like today, we don't know if quarks can be divided into smaller pieces because we don't have the instruments or the technology to allow us to look at that. Okay, so prior to Thomson, they just pictured an atom as being the smallest unit of matter on Earth. But Thomson, because of the law of electrostatic charges, discovered that there's negative charges and positive charges in an atom, okay? So Thomson's model had electrons, and he discovered that in 1897. So he predicted, or he theorized, that the electrons were just embedded in a sphere that had a positive charge. This is that plum pudding model that we were talking about with the blueberry muffins. If it helps you to think about like a chocolate chip cookie, where you've got like the cookie itself, and then you've got the chocolate chips. The chocolate chips are like the electrons floating or just embedded in the positively charged cookie. Okay, that's how Thomson theorized that atoms look like. Plum pudding being like you've got plums stuck in a dish of pudding. It's positive, yeah.
Well, we have to know the dates that they live.
No. Just, I want you to understand the progression, okay? I want you to think about the progression from like, okay, we've got atoms. Now we're discovering that atoms can be broken down smaller and they have charges. And then we discover the nucleus, okay? I want you to understand the progression, okay?
Can you tell us if it's gonna be like we have to write what they did or we have to it's gonna be math?
So I want you to know like Democritus came up with atomos, and that was in opposition to Aristotle, that matter can be divided indefinitely, which it can't, that we know of. All right, I want you to know that John Dalton solidified Democritus's ideas about atoms. Okay, and I want you to know that Thomson was credited with discovering the negative charge, okay, which is the electron. Yeah.
I thought Thomson was for negative and positive charges.
Yes. Yes.
Okay. And the DeMarcus guy, that's for he organized that the world is made up of tiny particles.
Yeah, that was the thing of the bread. You can cut it until it can't get any smaller. Okay. Versus Aristotle, who said you can just keep going forever. All right. So that's Thomson. Thomson was positive and negative charges. But he just didn't understand where the charges were at. He just said this is a neutral atom. It's got equal positive to equal negative charge in it. So then, the plum pudding model. So views atoms as spheres of positively charged material with embedded electrons.
We need to know that.
Yes. Yeah. All right. So Rutherford, Ernest Rutherford had this experiment back in 1911 timeframe, where he was shooting positive charges at atoms. And his theory was that atoms are mostly empty space. He found out, he was trying to see if you shoot a positive charge at an atom, if it looks like what Thomson theorized it as, that it's just this big positive ball of charge, that if you shoot a positive charge at it, it would repel it, right? But Rutherford found out that shooting it at the atom didn't necessarily repel it back. So he found out that this positive charge, instead of being all over the atom, was just concentrated in the middle. Because the only time that the positive charge that he shot at, the cathode that he shot at, the only time it repelled back was when it was shot at the middle. Okay, that's how he discovered the nucleus. So Rutherford, nucleus. Okay, and he used the gold foil experiment. The gold foil experiment is where he shot the cathodes at atoms. Okay. So Rutherford's model included a dense, positively charged nucleus that contained at least one proton with the electrons moving around it. That's known as the nuclear model for nucleus. Okay. So Rutherford equals nucleus. So we're progressing from Thomson's model that had positive charge all over with embedded electrons to, no, positive charge is just in the middle. Okay. So the discovery of the nucleus is a result of Rutherford's famous gold foil experiment.
So you basically just discovered the nucleus?
Yeah. Found out that all that positive charge wasn't dispersed all over the atom, it was concentrated in the center of the sphere. But what we didn't know yet, what we haven't figured out yet, we know that there's electrons in this atom, but we don't know what they're doing. Are they just hanging out? Are they moving? So that's where Niels Bohr comes in. This slide's in the wrong spot. I drove it out the first period. Okay. So Niels Bohr came up with this theory that electrons move around the nucleus in fixed circular orbits. You need to know the word orbit, just like a planet orbits around the sun, okay? So Bohr's model is based on this theory that electrons move in fixed circular orbits that are equally distanced around the nucleus. We use the Bohr model in teaching chemistry because it allows us to show how electrons are shared between elements when we talk about like ionic bonding. Okay. Ion meaning something that an atom that's charged, where they gain or they lose an electron. We'll get there. All right, so Bohr's model is based on that theory. We use it in class today because it's easy to teach off of. It's really simple to understand. Versus the quantum theory, where you've got electrons shaped in like tear-shaped clouds, right? It's really hard to teach off of that. So Bohr is credited with discovering the movement, really, of electrons. So from there, we've got physicists like Ernest Schrödinger, who's the next scientist we'll talk about. They learned that electrons don't travel in those cute little neat circles. That they travel like the guy in the video said, like those flies that are just going crazy. But if over time you realize that they're not just moving kind of randomly, that you can use math to calculate where an electron will be within that cloud. So if you're looking at the atom as a whole, you can use math. I don't know how. I don't understand this at all. But you can use math to calculate where an electron will be within that tear-shaped cloud, okay? So that's what Schrödinger figured out. So he found out, or he is credited with discrediting spherical orbits and replacing them with the idea of orbitals, those like tear-shaped clouds that electrons move in. So although this is the current model, there are still aspects of the Bohr model that still prove useful. Like it's kind of 2D shape. Easy to talk about bonding that way. Okay, so Schrödinger. This is kind of a picture of what his looks like, where you've got all the electrons are just moving however they want out here. You still have the nucleus, right? This is actually inaccurate because neutrons hadn't been discovered at that time, because James Chadwick discovered them later on. Anyway, so in Schrödinger's model, there is no definite position for electrons around the nucleus. But he developed mathematical equations to describe the probability of an electron's position or location. You don't really need to know that. Okay? So just know that Schrödinger discredited the perfectly circular orbits, and he came up with orbitals instead. Replaced orbits with orbitals. So in 1932, James Chadwick confirms a neutral subatomic particle, also known as the neutron. Yeah, neutron is neutral. So he discovered that this mass, that the atomic mass, it wasn't making sense. Okay? I don't know how he did this, what experiment he used, but he found out that there's more to an atom than just protons. There's something else in here. And he discovered that there was a neutrally charged particle in there called a neutron, located in the nucleus, and then it had a mass equal to that of a proton. Okay? And different isotopes of an atom will have different numbers of neutrons in them. We learned that yesterday. Okay, so that was James Chadwick. James Chadwick equals neutrons. So this is our modern quantum theory. These are these like tear-shaped electron clouds. All right, so we extend the electron cloud model to a three-dimensional space, and it now includes dense I don't know why it uses that word. I would say teardrop regions where electrons are most likely to be found. Okay, modern quantum looks like this, is all you really need to know. This is the most accurate view of what an atom looks like at this current time. But we know that models are always changing, always becoming more refined and more accurate. So just know that this isn't like a permanent thing, that I'm sure that advances in technology and experimentation will lead us to something that's more accurate than this. The more we discover, the more accurate it gets. Yeah.
What was James Chadwick?
James Chadwick was neutrons.
What about the, he discovered where they were?
He just discovered that they exist. Yeah. And that they were located in the nucleus. You're right. And their mass is equal to that of a proton.